Let me share something fascinating, something that kept me up at night when I first heard about it. April 17th last year, NASA released data that may represent the most consequential discovery in the history of science. Signs of life were detected on a distant planet called K2-18b, and not with some thin margin of uncertainty. The confidence level stood at 99.7%. That's not a rumor. That's not wishful thinking. That's a number that would make any statistician sit up straight. I've spent decades studying astronomy and astrobiology, and I can tell you, nothing in my career has felt quite like this moment. The planet in question sits 124 light-years away. Now, I know what you're thinking. Professor, that's impossibly far. Bear with me. Chemical compounds were detected in its atmosphere, compounds that, here on Earth, are almost exclusively produced by living organisms. What really knocked the wind out of scientists, though, was the concentration. These substances were present at levels roughly 1,000 times higher than anything we measure in our own atmosphere. If biology is behind those numbers, as it is on Earth, then we're not just talking about some microscopic sliver of life. We might be looking at an entire ocean teeming with organisms. And here's the kicker. K2-18b appears to be a water world, a planet draped in deep oceans, potentially harboring life unlike anything our biology textbooks have prepared us for. Now, let me take you back to where the story really begins. The year was 2015. NASA's Kepler Space Telescope had entered a second phase of its mission, known as K2, Second Light. During that campaign, it cataloged over 1,200 distant worlds. One of them caught scientists' attention immediately. Roughly 2.5 times Earth's diameter and nearly 9 times its mass, this peculiar object received the designation K2-18b. 2 years later, in 2017, the Spitzer Space Telescope confirmed something critical. K2-18b occupies the so-called habitable zone around its star, the narrow orbital band where surface temperatures could allow liquid water to exist. Almost simultaneously, astronomers at an observatory in Chile, working with a precision instrument called the HARPS spectrograph, measured the planet's density. The numbers hinted strongly at the presence of a subsurface ocean. The stakes, as my colleague once put it, were rising fast. Then came 2019, and the Hubble Space Telescope added another piece to the puzzle: water vapor detected directly in K2-18b's atmosphere. Hope at that point had become something almost tangible. The real turning point arrived in 2023. The James Webb Space Telescope, humanity's most powerful eye in the sky, turned its sensors toward K2-18b and detected something that stunned the entire scientific community: traces of dimethyl sulfide. On Earth, with only rare exceptions, this compound is produced exclusively by living organisms, particularly phytoplankton and other marine microbes. If the data was correct, scientists might have been staring at the first evidence of extraterrestrial life ever recorded. But here's where good science demands humility. One instrument does not a discovery make. The initial measurement had been taken with Webb's near-infrared camera, and distinguishing dimethyl sulfide from methane in that wavelength range is genuinely difficult. Could it be instrument error? A quirk of the detector? A reasonable scientist had to ask. NASA's response was methodical. Run the observation again. Use a completely different instrument. Apply a different methodology. If two independent systems returned the same answer, then the claim would carry real weight. On April 17, 2025, that second observation was completed. Webb's mid-infrared camera, a distinct instrument from the one used before, scanned K2-18b in detail. The result, dimethyl sulfide, confirmed again, and that concentration figure, roughly 1,000 times Earth's baseline, held up. So what exactly is dimethyl sulfide, and why does it matter so much? You know what's interesting? If you've ever walked along a coastline on a windy day and caught that sharp, briny smell rolling off the water, that's largely dimethyl sulfide at work. It forms when microscopic algae, phytoplankton, and other marine organisms break down. As they decompose, this compound is released into the air. Here's what makes it a genuinely remarkable biosignature. It's chemically unstable. Sunlight and oxygen destroy it rapidly. It cannot simply accumulate and linger. It requires continuous replenishment. On Earth, that replenishment comes almost entirely from biology. So when astronomers see a 1,000-fold enrichment of this compound in a distant planet's atmosphere, the logical question becomes, what's producing it? If the source is biological, as it is here, then not only does life exist on K2-18b, it must exist on an enormous scale to sustain that concentration. Detecting any of this from 124 light-years away sounds like something out of a science fiction film. But here's the method, and it's genuinely elegant. As a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching us. That atmosphere acts like a fingerprint scanner. Different gases absorb different wavelengths of light. By studying those absorption patterns, astronomers can essentially read the chemistry of an alien sky. It's like the planet is leaving us a note, and the Webb telescope has learned how to read the handwriting. Now, to fully appreciate what might be happening on K2-18b, you need to understand its environment. The planet orbits K2-18, a cool red dwarf star. Its orbital path is tight, about 2.5 times closer to its star than Mercury is to our Sun. But because red dwarfs are considerably cooler and dimmer than our star, that proximity works out to roughly the same energy budget as Earth receives from the Sun. A delicate cosmic balance. Scientists categorize K2-18b as what's called a Hycean world, a hypothetical class of exoplanet proposed in 2021, potentially covered by a vast ocean beneath a thick, hydrogen-rich atmosphere. Supporting this classification, no ammonia was detected in the atmosphere. Ammonia would simply dissolve into an ocean if one were present. Its absence speaks volumes, and yet, and I want to be honest with you here, serious doubts remain. If the planet truly is ocean-covered, those oceans might be extraordinarily hot. Not the kind of environment that supports life as we understand it. Temperatures, pressures, and chemical conditions could transform those waters into something far more hostile. There's also a genuine scientific debate about whether K2-18b is even a Hycean world at all. Dr. Nicholas Vaughan of the NASA Ames Research Center, among others, argues the planet could instead be a miniature gas giant, lacking any solid surface whatsoever. In that case, the probability of life drops close to zero. On the other side of that debate stands Professor Niku Madhusudan of the Institute of Astronomy at the University of Cambridge, the lead researcher behind the dimethyl sulfide detection. His team's analysis points strongly toward an ocean world, and he believes life is a genuine possibility. According to his timeline, within the next 1 to 2 years, scientists should be able to determine with very high certainty whether dimethyl sulfide is genuinely present and whether its origin is biological. That 99.7% confidence figure currently reported represents the highest level of certainty ever attached to a potential biosignature beyond Earth. But Cambridge researchers are deliberately cautious. Before declaring a discovery, they need to confirm the gas at an even higher threshold, around 99.99%, and then separately establish that its origin is biological, not chemical or geological. If that confirmation comes, the implications are staggering. Not just the fact of life existing elsewhere, but where, a mere 124 light-years away. In human terms, that's an incomprehensible distance, roughly 1,174 trillion kilometers. Even reaching Mars remains a monumental engineering challenge, and interstellar travel may forever lie beyond our reach. But measured against the full scale of the cosmos, the universe stretches 93 billion light-years across. Finding life at 124 light-years would be the equivalent of searching your entire house and discovering what you were looking for was sitting in the hall closet all along. It would suggest that life isn't a cosmic fluke. It would suggest that if it arose there, it could have arisen almost anywhere. Let's take a moment and use our imaginations, something scientists do more often than people realize. What might life on K218b actually look like? The simplest forms would come first. On Earth, everything began with microbes, and the same logic almost certainly applies there. Organisms capable of thriving in a hydrogen-heavy atmosphere under intense pressure and elevated temperatures. Think of Earth's extremophiles, those remarkable microbes living near deep sea, hydrothermal vents where temperatures exceed 100 degrees Celsius, and chemical reactions replace sunlight as an energy source. On K218b, hydrogen atmosphere chemistry and possible volcanic activity could support exactly that kind of biochemistry. If evolution went further, the shape of complex life would be dictated entirely by environment. Deep beneath a thick atmosphere, light would be nearly absent. Vision, so central to life on Earth, would likely be useless. Sensation through vibration, heat gradients, and magnetic fields might dominate instead. Some organisms could potentially develop bioluminescence, producing their own light as certain deep-sea fish and jellyfish do here. The hydrogen-rich atmosphere is particularly interesting for questions of size. Hydrogen is lighter than air. Buoyancy in such an environment would be greater than on Earth, potentially favoring the evolution of very large organisms, slow-moving, massive creatures adapted to extreme pressure and dense water. Picture something like an enormous jellyfish or a vast, formless entity drifting through warm ocean depths, or perhaps even through the atmosphere itself. Pressure adaptation would be paramount. K218b's ocean may be far deeper than Earth's, with some zones potentially experiencing pressures between 1,600 and 2,000 atmospheres, far beyond what our own Mariana Trench can produce. Surviving that would require biological materials of extraordinary density and resilience, exoskeletons built from biopolymers several times stronger than anything in Earth's biochemistry, protective shells that both resist and distribute crushing force. Of course, all of this is speculation grounded in analogy. We don't know what chemistry drives metabolism there. We don't know what molecule plays the role of DNA. But if the dimethyl sulfide being detected truly is biologically produced, then something is alive on K2-18b, something that has adapted, evolved, and persisted. And that is almost certainly entirely unaware that a 70-something professor on a small rocky planet 124 light-years away is standing in front of his students, talking about them. Now K2-18b is the most exciting candidate we have, but it isn't the only one. Let me quickly walk you through some of the other fascinating worlds worth watching. T-Garden b sits just 5 light-years away, practically next door in astronomical terms. Scientists estimate roughly a 60% probability that it hosts Earth-like conditions, moderate temperatures between 0 and 50 degrees Celsius, likely liquid water, reasonably stable climate. The catch is tidal locking. One hemisphere permanently faces its star in perpetual daylight, while the other sits in endless darkness. Life's best opportunity might exist only in a narrow twilight band between those extremes. Kepler 1649c, discovered in 2020, is 301 light-years away in the constellation Lyra. It orbits a red dwarf 5 times less massive than our Sun and 4 times smaller. The planet itself is only about 6% larger in radius and 20% heavier than Earth, meaning gravity there would feel almost familiar. Like T-Garden b, it's probably tidally locked, but that same terminator zone between light and dark sides could maintain stable Earth-like temperatures and possibly liquid water. TOI 700d, found in the constellation Dorado, roughly 101 light-years out, stands apart for a particularly hopeful reason. Unlike the previous two, it may not yet be tidally locked. That would mean genuine day-night cycles, creating a more climatically stable environment. It receives about 86% of the solar energy Earth gets, and surface temperatures are estimated around -4 degrees Celsius. Cold, certainly, but nothing a greenhouse effect couldn't soften. Its star is notably calm for a red dwarf, producing far fewer violent flares than most, which dramatically increases the odds of a long-lasting atmosphere. That stability matters more than most people realize. And then there are the genuinely alien worlds, the kind that seem to belong to science fiction. J1407b, located about 434 light-years away, is essentially a supercharged Saturn. Its ring system consists of 30 individual rings, each tens of millions of kilometers across. The entire structure spans roughly 120 million kilometers in diameter, 200 times larger than Saturn's rings. If that ring system surrounded Saturn instead, it would dominate our night sky like nothing else. Given time, those rings will thin as moons form from the material, but right now it's one of the most visually spectacular objects ever catalogued. At the opposite extreme is Kepler 70b, 650 light-years away in Cygnus. This is a planet that survived inside its star. When Kepler 70 went through its red giant phase 18.5 million years ago, Kepler 70b, then a Jupiter-sized gas giant, was engulfed. What remained was essentially the iron core, a scorched remnant orbiting 65 times closer to its star than Mercury orbits our Sun. Surface temperatures reach 6,650 degrees Celsius. For comparison, our Sun's surface sits at around 5,500 degrees Celsius. Yes, this planet is hotter than a star. If there is a hell somewhere in the cosmos, Kepler 70b has a strong claim. Finally, there's KOI 5AB, a planet remarkable not for its own properties, but for the system it inhabits. Roughly half the size of Saturn, it orbits one star of a triple-star system. Stars A and B circle each other every 30 years, while a third star, C, takes 400 years to complete its orbit around the pair. Standing at the edge of KOY 5AB's atmosphere on a spacecraft, you'd look down at dark brown and gray clouds and up to see not one sun but two, one 17 times larger than ours, the other dimmer, yet still 1,000 times brighter than a full moon on Earth. The universe, I've learned over my career, is under no obligation to be ordinary. Every time we think we've mapped its possibilities, it hands us something we never imagined. We catalogued all the planets in our solar system over centuries, and they still surprise us. More than 5,000 exoplanets have been confirmed so far. Humanity has never stood closer to answering the question that has haunted every civilization in recorded history. Are we alone? The answer, it seems, may be sitting in the atmosphere of a water world 124 light-years away, quietly exhaling a gas that smells like the ocean.